But I'm going to focus on the physical climate system and focus predominantly on observations and the data they create and where we've been and what the challenges I think are ahead. And so I'm not sure what you're seeing, but I've got slide numbers. And if you can push on to slide 3, perfect. I'll talk a little bit about the evolution of my career and what I saw. And I think it's actually pretty amazing. If you look back in the 1970s, I mean, at that time, global temperatures, we really didn't have a good handle on long-term changes in global temperatures. And back in the 70s, we primarily had northern hemisphere temperatures. And then in the 80s, we really had our first attempt at trying to put together a truly global picture, but really they were driven by a lot of subjective assessments as to how good the data were. Going into the 90s, this is on slide 4, that's where we picked up the objective methodology to really assess what I would call time-dependent biases. And then we got, I think, fairly serious about trying to put error bars on our global temperatures. And there was still quite a bit of controversy, is the globe still warming or not? But during the 90s also, interests then became evident in not just the mean temperature, but what are the max and min temperatures doing, and many other variables. And that's when the global climate observing system concept began, and the concept of essential climate variables came into vogue. I remember one of the United Nations Framework for Convention on Climate Change meetings where the ECVs got adopted, and they really took hold, I think, across many nations. And that's really when IPCC began to engage all of the various communities in science, the global change science, and that's where the data sets, I think, really had the people putting together the data sets really had the motivation to put things together that could be viewed by not only their discipline but other disciplines. Then if you look at the 21st century, I moved on to slide 5. What I would say happened in the 21st century, we really matured the concept of climate data records. And what I mean by climate data records is a great attention to version control, research to operations, because these data sets needed to be updated on a regular basis. There was a lot of interest in what was happening, not just 3-4 years ago, but what's happening today compared to the last couple of years. Reproducibility was extremely important now. We had to be able to show not only the data, but how you could come up with the same answer that we come up with. Transparency, the whole notion of scientific data stewardship. So I think that was a major advance in the first decade of the 21st century. What also became evident is that we had much higher resolution, both daily data and much better spatial resolution. One of the things that's happened the last couple of years is because of the predominance of the increased resolution of the data, the attention to climate data records, we now can actually look by year and talk about whether or not the weather and climate extremes that we've seen in the past year were driven primarily by natural causes, human causes, or a combination of both. And I think that's a major step forward to be able to do that on an annual basis. State of the Climate reports published every year in the Bulletin of the American Meteorological Society has 250 authors, 60 countries. So this is in addition to the IPCC reports that are done every 6 or 7 years. This is a very helpful exercise to make sure we're as up to date as possible. We have something called reanalysis that has really changed the way we look at observations. That is, taking all the observations and putting them into a comprehensive global climate model so that we can actually get the best of both worlds. That is, observations that then can be harmonized through the understanding of the physics and chemistry and thermodynamics in those models. And so that's enabled us to look at some things in terms of changes and variations that we might not otherwise have been able to do. We've got some new objective satellite-derived and in-situ data sets, things like hurricane intensity, precipitation extremes, sea level, monitoring, global monitoring of droughts. So we've got just tremendous amount of information that's exploded on this scene in the last few years. Ice sheet content, thickness, because we've got satellites now that we didn't have, just amazing differences. On the next slide, slide 6, because of the increase in high resolution data, are we on slide 6? Okay. The notion of trying to understand the whole probability distribution function and where it is. And there's still a lot to learn here, a lot of exciting opportunities when we talk about the extremes and where we're headed on the tails. And I'll just go on to the next slide. I mean, Jim Hansen had a very, well, still does, but had a very nice paper that came out a couple of years ago, just showing what you can do with the observations and data we have today by showing what happened in the decade of the 1950, or the decades from 1951 to 80, and where the globe, in terms of if you decompose it with 5x5 grid cells and look at where they fall in terms of a mean climate, you can see in the period 51 to 80 pretty much a nice normal distribution, and you can see how it slides to the right. 2001 to 2011, you can see the frequency of very, very warm temperatures in the order of several standard deviations above what the mean would have been in the 50 to 80 period, happening much more frequently, 10% versus 0.1%, pretty drastic changes. And I think there's a lot to be learned here, because there's some evidence to suggest that temperatures aren't always normal. And you're talking about the extremes, that's very important, both in terms of the extreme cold and extreme warm periods. Now with daily data, we're going to be able to look at that much more closely. Next slide, slide 8. We already know there's major signals with extreme precipitation. This is the U.S. showing large increases in extreme precipitation events in the eastern half of the U.S. Next slide, slide 9. Some of the things we can do now, a recent paper published in Nature by Jim Cosson and some of his colleagues. We can now look at the tracks of hurricanes, showing their northward migration in the northern hemisphere. These are hurricane tracks, the southward migration in the southern hemisphere, and you can see the difference at the very bottom. These are signals we would never dreamt that we could discern years ago, and I think this is really important because it changes the debate on hurricanes to be not only focused on the intensity, but the tracks in terms of where they're going to be. If they're moving northward, that could mean some areas that haven't seen hurricanes may be subject to them. Other areas that have been used to them may see them less frequently. A whole nother interest for our community. The next slide, slide 10. This was put together by a whole series of papers published in the Bulletin of the American Meteorological Society. A number of people got together from the standpoint of the National Climate Assessment that was put out recently. I know Don Weebles is in the audience. Don was a key participant in putting this diagram together. Taking a look at extreme events. This is only for extreme events, and you see the different phenomena from extreme precipitation in the right, heat waves, cold waves in the upper right. down to the bottom, thunderstorm winds and ice storms, where we looked at, and this is a subjective assessment based on probably 100 or so scientists, looking at if we can detect changes in these extremes and whether or not we know why their changes are occurring if we can detect either an increase or decrease. And you can see for, in general, for most of the time, if we've got better information to observe, we've got a better understanding. Now, that doesn't always apply, but in general, you can see as you get more knowledge for detection, the chances are you're going to understand the cause. And I think this is the value that observations bring to the table. On the next slide, um, uh, I think where we're going in the future is not just daily, but sub-daily information. And I'll show you a few examples. And I think this is really going to be fascinating. Um, I think we're going to be on the verge in just a few years of being able to look at hourly extremes of things like precipitation. And we're already seeing work showing that there's some interesting things that are potential here. The Clausius-Clapeyron relationship may have some different ways of operating when you bring in, well, put it this way. The Clausius-Clapeyron equation is really important in terms of trying to understand how much water vapor gets converted into precipitation in potentially extreme precipitation events. And normally, if you had a 1% increase in water vapor, you'd expect, about a 7% increase in precipitation or extreme precip events. And that's kind of what we see at the big picture. But when you get down to the smaller space and time scales, that doesn't seem to hold. And there may be other factors that are more important. And so I think this could have some major implications in terms of how we understand how the climate system works with respect to increasing water vapor, higher temperatures, and higher precipitation rates. Non-normality of temperatures, I think that's going to be a very interesting area. And the reason why I think we're going to get a lot of new data, you go to the next slide, slide 12. This is an example. This is for U.S. Doppler radar data. There's a major effort now that's just about finished reprocessing all the radar data. Is about 12 years of data, and it gives you 1 kilometer, 5-minute data across the U.S. Going back to 2000. This, when combined with in-situ data, satellite data, really, I think, is going to change the way in which we look at our analyses. And not only does the U.S. have very good radar coverage, but many other countries do as well. This is going on in Europe, Australia, Canada. There's tremendous potential for increased space and time resolution. I think we're going to learn a lot. Next slide, slide 13. Some of the major influences that I've seen that affected me and I think affected the whole community. Obviously, WMO has been extremely important. I think we can't underestimate the importance of that international activity, the basic exchange of data and information, especially making data as openly available as possible. We have to continue to push on that. IPCC, all the physical climate assessments and all the other assessments. The national assessment has been important, I think, particularly for me, all three of them. The US GCRP, and particularly now looking at it from a different side, has been really important. And the Aspen Institute, the AGCI workshop on extremes was particularly valuable for me. I think it really kick-started a lot of the extremes work. And for me, one of the things that sometimes you learn from your mistakes. We tried to do a climate service in NOAA a few years ago, and that didn't work. But I think there's some lessons learned there that we need to take advantage of. The next slide. That's perfect. Big data, I think that's really going to be extremely important. And the big data aspect is to try and make sense out of all this data we have in ways that uh, we don't have to, go through petabytes of data or gigabytes of data, but being able to try and provide the data in a much condensed form, I think is going to be really important. Another issue I think that we've got to worry about is the expectations with respect to downscaling information, both in space and time, has far exceeded our ability. Despite all these advances, I think the community out there has expectations of what you can do with downscaling in terms of future and predictions that are a bit unrealistic at present. The next slide shows the volume of data as it's changed in the past. So a lot of data out there, a lot of people using it. We served just at NCDC over 5 petabytes of data last year. That's almost a Kindle book for every person on the planet. The next slide, where are we going? You can see the exponential rise continues, and it's largely driven by satellite data, but model data you can see in the out years becomes a close competitor. Some of the data compresses much better, and the cumulative number there, what you see is uncompressed. But if you can compress the data, I think the technology is easily going to keep up with the amount of data we can record. The next slide. What is it that I think has enabled our progress? And I think it really is the fact that we have had cheaper data storage. We've got better observing capabilities. We've got great ideas like Earth System Grid, Global Change Information System, ways in getting access to model data and observation data that is much easier for users than it was in the past. We've got some cloud solutions emerging for processing. And I'll show you on the next slide what's really remarkable in terms of our advances in computational capability. And lastly, I just wanted to mention this slide is major concern still is difficulty connecting across disciplines and institutions. I think that is still work to be resolved. The next slide shows back in the 90s when we tried to reprocess, this is slide 18. Slide 18, we tried to reprocess the AVHRR satellite imagery. It took about 3 or 4 years. Using the cloud, and here's an example, we reprocessed 31 years of data in 1 day. So imagine 3 years versus 1 day today. If you use the cloud appropriately, here's a number of instances, number of machines that you employ. You can see if you get up to 120, you get a sweet spot. You can process all the data in a day. If you don't optimize, it's a little more like 400 days, but that's just amazing. You'll be able to reprocess a data set in 1 day that took us several years, just 15 years ago. Global change research, next slide, slide 19. What lessons would I draw on for the future? I think new science capabilities for monitoring, understanding, predicting, I think that's going to be increasingly provided by the technology breakthroughs, but there has to be adequate capacity on the science side to be able to appropriately put all that data and information together in useful format. I think in the last slide, I'll just end with in the future in terms of the challenges for the next 10 to 20 years. I think we're going to be challenged by temporal gaps in observing systems. And I think the real issues are, I think we'll solve the potential gaps in the big satellite programs, get a lot of attention. But I think the low and medium technology observing systems that are key are going to be difficult to maintain at the current rate. I think there's going to be key for us to really focus on seasonal to decadal predictions. I don't think we're going to get away with being able to just talk about 30, 40, 50 years from now. People are going to want to understand how are we going to get from here to there. And unfortunately, that's where our skill isn't quite as good because the forcings aren't quite so obvious. A major challenge for us, water cycle, and I think assessment science is a growing necessity. So with that, maybe I'll leave it for a few questions, James.
The weather here is changing quickly, but we have about 7 minutes for some questions. Sherry?
Yes, I've longed to ask you this question. You spoke about the non-normality of the temperature extremes, and we were designing a test question for this concept inventory on climate change related to extremes, and what would happen if you increase the global average temperature, what happens to extreme cold events into heat waves, right? And the sort of nominal answer, of course, is that you shift that distribution and you get more heat waves and less cold extremes. Over 40% of our students, including a lot of students who otherwise did well on this concept inventory, there was this idea.
Come up.
Okay, I'll see. Back in. There was this question of being lots of students answered the question, no, climate change, no, oh my goodness, it's going to be both extreme cold and extreme warm. So that notion we discovered by testing this question is a lot out there. Is it possible, is the question, to make the distribution, to have a big standard deviation, to change it in some way that would permit that answer to be correct, that you would have extreme heat waves and also extreme cold in greater frequency?
So if I were teaching 101 class, I would just say yes, the whole distribution moves over as a first order answer. Where the interest is that what you find is geographically and in different seasons of the year, that distribution doesn't look quite so normal, and it's geographic and seasonal dependent. And so then when we start talking about changes, then we've got to understand how that distribution could be affected differerentially. And quite honestly, I think this is, some people may say, well, it's a little bit a second order question. Yes. That is, the first response would be, yeah, the whole distribution shifts. But the reality is, if you look closely, and I'll give you some examples, if you look at the Dakotas in the wintertime, look at the extreme tail on the left side, cold. It's not normal. It's cold. We get these far extreme cold events. And when you look at almost the same area in the summer, you look at heat waves, you can get the extremes on the other side. And a lot of times it's these feedbacks, these land surface feedbacks. So why that's important is because if you're really looking at these extremes and are really important, you'll want to understand that. But as a first answer to 101 students, that's probably a first order just answer.
Tom, just to add to that, this is Don Webbles. We just did some analyses looking at the shifting, but focusing down to the U.S. CONUS does pretty much the same kind of shift, although not as large as globally, as what Jim Hansen saw. And then if we went down to the Midwest, because ag people were asking about this, we really don't see this as much shift. There's been very little shift in the extreme heat events. And it kind of goes along with what we thought was going on, but it really shows up very clearly when we really analyze the data.
Yeah, because it's been so wet in the Midwest for the last couple of decades, that land surface just, is really important in the summertime.
Yeah, exactly.
Yeah, Roger. Yeah. Hey, Tom. It's Roger.
Hey, Roger. Well, you're there and I'm here, so I don't know. That's
substitute as ineffectively as I can. Okay, so here's a question. I fully agree on assessments and science, understanding the water cycle, seasonal to decadal. And I would like, to give a pitch, not to give you a softball, but we have a serious issue with declining in-situ observing systems. And I'd like to know what you think that the global change community can help, with the ways they might help in sort of helping to alleviate that problem. The satellites are great, modeling show that even adaptation practices are delayed if you don't have a critical network where people can see the changes. So from the standpoint of AGCI and this group, and GCOS and a few other things, what's the case we can make that in fact declining networks of in-situ odds are a critical development, adaptation, preparedness gap?
So that's a great softball, Roger. Thanks for that. I owe you a beer next time I see you.
Good bottle of wine.
Well, come to Asheville. We've got so many microbreweries now, to believe. But what I think, here's where I think the problem is. We have had, we've segmented the community into satellite community and in-situ community, which really, we lost our way because when GCOS first started, we talked about essential climate variables. And if you talk about, for example, if you want to measure water vapor and you were saying that is my key goal, you wouldn't only think about putting forward a satellite observing system, you would have all the components there, and that's what you would articulate and argue for. So I think we as a community have to try and avoid the separation of observing platforms driving the resources as opposed to the variables you're trying to get to. So, for example, if it's some issue that is being driven by dollar, quite honestly, it comes to dollars and cents. Aerospace industry has a lot of motivation for lobbying up on the Hill for major observing systems. So I think our responsibility is to try and show those resources aren't as well spent because they have to be validated by in situ in many cases. So I think we really have to push that. And if we could, we might be successful.
Thanks. Okay. And last question goes to Jerry. Maybe just come here and speak.
Hey, Tom. So I guess you mentioned the 1998 extreme session, which I also mentioned in the historical overview as being a kind of a critical turning point for the field. And I think one of the aspects of that session was we had the observations, we had modeling, we had impacts people, and we had all the communities that were kind of involved with global change science at that point, with observations being a big part of it. Since then, and you've worked to now at the highest levels of the federal government on this problem, what do you see as a critical need in terms of communities that still need to connect, or we need to connect better with in terms of climate observations and the other areas of global change research? I mean, are there certain communities that you're thinking of targeting or think you have in mind that we haven't connected with yet, that we still could or need to connect to?
Well, one thing I did cut my last slide off, so now you asked me the perfect question. I can get to that one. I think what we need a new breed of scientists now that have their foot in both doors. One door is, they're well trained in physical sciences or social sciences, but they also can navigate the user world. The user world that I'm thinking here is not simply governments, but private sector. And I think that's a specific breed of people that actually could help us think about what we do and why we do it, and maybe help from the standpoint of Roger's questions as well. Because I think right now, we have a lot of people who are very interested in putting together the data sets and looking at the models and doing the intercomparisons. And I see people in the private sector, working in their world, but we don't have a good bridge. And I think that's a piece that's missing. And if it were really to take off in the next 10, 15 years, I think it could be a big boon to both the science side and the user side. I don't know if that's what you're seeing, Jerry, as well, but I think that's a missing piece still.
Have good input for this workshop, actually, what we're going to be trying to put together at the end.
And a PS from Richard.
Yeah, hey Tom, great talk, thanks for doing it. Just one follow-up though on this. I agree with the point you just made, but I also want to, and I know you'll agree with this as well, put in the plug for AGCI and other mechanisms like that. Because some of the issues that we're confronting are really multi-community issues. And yesterday we had a really interesting debate on one which I know you're aware of, and I'm just curious to know whether there's any further thinking on it. And it just has to do with the issue you talked about, downscaling and managing user expectations. But from the science side, of course, there are all sorts of trade-offs, you know, higher resolution, increasing complexity with more processes involved, higher number of ensembles, you know, and there have been some proposals for workshops and so forth to have, you know, real broader scientific community debate on managing those issues. I'm just curious, in the spirit of something like AGCI, whether you see any opportunity for further debate about that.
No, absolutely, absolutely, Richard. And I'll give you an example. I mean, we're working with, and I won't name the agency, one of our sister agencies, and you know they're very concerned about their infrastructure at specific locations. And we were talking to them about extremes of precipitation. They said, yes, but we want to know it for, you know, and their little plot of 20 acres. And you know, I think you know, it's unrealistic expectations in terms of what we be, you know, that we're not going to be able to give them anything different there than we would on a much larger space scale. Now you could try and tailor it to the topography, but that topography is not going to change in 50 years. So my sense is, I think there is a lot of room here. I think the Aspen Institute here, Global Change Institute, could really help, because I think it's an opportunity to bring people together with different backgrounds, and that's really what's needed.